Alright, this video is going to try to give you some help with the mole ratios lab. I just want to remind you about the introduction because I know it's been a while since we've done this lab. That basically the coefficients in a balanced chemical equation show you the ratios of the reactants, how many moles of each reactant you need to combine in order to make certain nanomoles of the different products. And so what we are trying to do in this lab is determine what that ratio is between the hypochlorite and the thiosulfate. So we did this by varying the amounts of each reactant that we added. It's called continuous variations. We kept the same volume in large part because if we keep the same volume, we don't have to account for the fact that they might have started, or that, excuse me, if they had started at different temperatures, that might have affected how much heat was generated. We also did that in large part so we could compare our data points to one another. That's why we didn't do 40 of solution A and we did only 5 of solution B. We wanted to keep that volume amount consistent so that when we compare the moles of the reactants, we can compare them across the board of the different trials. Because it was exothermic, we could use temperature change to determine which combination of reactants would give us the most bang for our buck, would provide the most energy, and therefore would allow the reactants to be consumed as completely as possible. I did this one summer in college when I was working in a pharmaceutical company where I varied different factors with a reaction trying to figure out which one would give us the optimal amount of product, because obviously pharmaceutical companies want to make the most product they can and be the most economical in the process. Alright, so with that in mind, you collected data. Again, make sure you have your heading in your data table in your lab book. So you won't necessarily have every row of this completed. I know a couple of you will, but you want to have whatever data you collected in that chart. And then we already graphed our data. We just use the volume of NaOCl on our x-axis. If you want to write the volumes of Na2S2O3 underneath that, you can. Keep in mind that when you had 0 of this one, you had 50 of the Na2S2O3, and vice versa. If you had 50 of the NaOCl, you would have had none of the Na2S2O3. Your graph goes in your lab report. It says it should be drawn to scale and put in your lab notebook as well. If you want to either photograph or if you want to sketch it, as long as you have made a good faith effort to sketch it, like with a ruler, I'm good to go. Again, this one I do want you to take up a little bit more room, so this one should take up about half a page in your lab notebook. Okay? Remember, when you are finished, you did these graphs in class, but I said you need to sketch the lines in using a ruler. If you notice here with this one, because the 2 points that were the highest were close together, the first line was put through the points that were all increasing, and then the second line was put through the points that were roughly at the same height that were decreasing. So you do not have to try to attempt, nor should you try to attempt to get whatever your highest value is in both lines. Which one does it make more sense in? Put it with that one. See which dot, whether it fits better with the line going in with a positive slope, or does it fit better with the line going with a negative slope. So like if I look at this data, if I try to put this point in, it just doesn't really make sense with the rest of the data. And if you're not sure about how to draw these lines, yes, you are welcome to come see me. This lab will not be due until next Monday, which I believe is November 2nd, which is when we'll be doing another lab again. Okay? I'm guessing the other video is ready to go now. So with that in mind, if we go back to our questions, it says, what is the optimal volume ratio of the 2 reactants? So which one gave us the greatest temperature change? And then I want you to give me evidence to support it. So tell me, based on your data, which of your ratios, and it says which is the optimal volume ratio, so we're not just referring to the data table. You can refer to anything on your graph to represent that optimal volume ratio, and then tell me why you picked it. That's all I'm asking for with the evidence. Again, that pre-lab question should kind of help with this. It says how many moles of the NaOCl solution are used at the optimal ratio. If you go back, you will see that the concentrations of your two solutions were 0.50 molar, and then we know based on the graph what the volumes were of those solutions. And so if you want to find moles, you're going to use molarity and volume to help you find that. As a quick reminder, molarity is the ratio of the moles of your solute, which would be the NaOCl or the Na2S2O3, in a given liter of solution. So if you have milliliters, you're going to have to convert to liters. And in order to find moles, if we hide the moles part, we see that it would be molarity times liters. So you're going to need to multiply your molarities times your liters to get the moles that would be present in that optimal mole ratio. So you'll do that for both reactants, and then once you have the moles from number 3 and number 4, you're going to divide them. I don't care which way you divide, whether it's the NaOCl over the Na2S2O3 or vice versa, but I do want to make sure that you realize which one you're working with, and then round it to the 10th space, or 10th place. So if you get 2.05, round it to 2.1. You get 3.87, you'd round it to 3.9. The next questions are dealing with the data that you had in the lab. The molarities of the reactant solutions were equal. Is this necessary or even important for the success of this experiment? Well, the goal for this experiment was to find that optimal mole ratio, and we're using volumes to help us do that. So what I want you to think about with number 6 is how did the molarities help you get your data for 2, 3, and 4? And is it critical that they be the same in order to get that kind of data? That's for you to tell me. Same thing for number 7. It says the combined volume of the reactant solutions was equal in this experiment. I talked to you a little bit about that when you were collecting your data. The volume combined of the two was always 50 mils. It didn't matter which combination you had. And we measured the temperature change associated with that 50 mils. What I want you to remember about temperature is that it is an extensive property, and that the temperature change is going to be dependent on how much of those materials that you have. So just something to kind of keep in mind. Which solution was the limiting reactant? If you've been doing the other videos for class, you know the limiting reactant is the reactant that gets consumed first. And so which one did you run out of going on the upward slope of your graph, and which one did you run out of going downwards on your graph? So again, if we look at this pre-lab, we see that we started out with no silver nitrate, so silver nitrate would be limiting. And then as we went up, we went to 5 to 45, so we had less silver nitrate, and we had a smaller mass of precipitate, and we kept going up. And then when we finally came back down, now we see the silver nitrates dramatically increasing, while the potassium chromate is decreasing. So on this graph, silver nitrate would have been the limiting reactant going up, and potassium chromate would have been the limiting reactant going down. So hopefully that helps you with numbers 8 and 9. Number 10, what is another physical property besides temperature change that we could measure in a lab where we varied the amounts of the reactants to determine which ratio would give us our optimal ratio? I will not let you use also the mass of the precipitate because that was given to you in the pre-lab. But anything else you want to come up with that would be some sort of property that you could measure that would not change the products being formed into something new is fair game for number 10. Number 11, why is it more accurate to use the point of intersection of the two lines to find that optimal mole ratio than the ratio that's associated with the greatest temperature change? Again, I'm going to kind of go back to that pre-lab. You notice here that the amount of precipitate that maximized on the left side of the graph was around 10 grams, and then that was around 30 mils of silver nitrate, and then it was also really close to 10 grams at 35. Well, if you do these in 5 mil increments, and maybe if you skip over 5 and do a 10 mil, what happened between that 5 to 10 mil increment? We don't know for sure. In this particular one, it turns out that the optimal ratio is pretty close to 33, 32.5 as opposed to at 30 or 35. In some, it might be closer to a whole number, but it's not necessarily going to be. So that's what I want you to think about, is that we did our volume measurements in 5 mils, or sometimes 10, 15. We want to know why we would pick one that didn't necessarily get measured to be our optimal mole ratio in that last question. So think about that, and again, if you have questions on this lab, I will be available to answer those both Wednesday and Friday.